Okay, so let us do a strategic review of Section 12 control systems. These are the four major areas that you are expected to know when it comes to control systems. Control systems is an interesting section because a lot of power systems engineers, I find, especially those who have the option of just focusing on power systems in their third or fourth year of undergraduate studies, sometimes lack coursework in control systems. Now, the FE Electrical and Computer Exam specification is not focused simply on electrical engineering or computer engineering or controls or software. You essentially need to have a decent understanding of a much more broader curriculum. And that typically is the case with most of the graduates who go to schools in the US, but I have a lot of internationally trained engineers who join my program as well. And the general tendency I've found is that folks are able to sort of focus and specialize in particular disciplines and sub-disciplines even in undergraduate. So the content that I've provided you guys in the on-demand course, tons of lectures, quizzes, mini exams, computer simulated practice exam, and the study guide, if you're using it, and the homework assignments and the live training broadly covers all the topics that you, in my opinion, when you go through it, you'll feel a lot more confident, even if you haven't taken any coursework. So block diagrams, as I explained in the course, are essentially like your single line diagrams for power systems, right? The most important block diagram, which thankfully they've provided in the reference handbook, is a classical negative feedback control system block diagram. I strongly recommend you to go through that 5-minute derivation that I've done in the course to get a sense of how you basically move around, how you label E of S, how you take care of the negative feedback, how the blocks multiply, and how you can turn off the external disturbances, and eventually how you come up with the transfer function y of s divided by r of s. Extremely important. Go through it once on your own and you will feel a lot more confident. The other aspect of block diagrams is simplification. Now, the handbook itself does not necessarily have any details around it, but when you look at the NCEES sample exam for FE Electrical, the paperback, they have come up with the interactive practice exam as well. But the paperback practice exam has a problem dealing with simplification of block diagrams. So please make sure that the discussion that we've had around series, parallel arrangement, branch movement, summer subtractor, that you understand it and are able to apply it properly in order to simplify block diagrams. And the reason why we want to simplify block diagrams is the same reason why we like to simplify digital circuits. It's the same reason why we use Thevenin theorem and Norton theorem to represent an entire mishmash of a lot of different moving pieces into a black box with much more simpler elements to deal with. Bode plots, they come in two different forms, basically. You have the magnitude and the phase plot, explained in a lot of detail with 6 or 5 different scenarios in the on-demand. So you can break it down into individual pieces, as we've seen earlier. It all starts with identification of poles and zeros. If you're not clear about what is happening when a pole is introduced or a zero is encountered, you do not stand a chance to have a shot at the transfer function or to deal with the Bode plot problems. Okay. The definition of pole zero is very simple, straightforward. And at the very least, you should be able to identify poles and zeros on a Bode plot. And the next step from there is to come up with a generic equation of the transfer function. And then the final step is to figure out the value of K, which is a steady state gain. And as I mentioned earlier, you can even be given a transfer function and you might have to reverse engineer the transfer function into a Bode plot. Okay, so everything is possible. So when we are dealing with Bode plots in the context of filters, if you guys remember, Remember that when we are encountering the active filters, we were dealing with 3 dB frequency. So that is an example of application of Bode plots that we saw earlier in the context of resonance, in the context of creation of filters, first order filters, second order filters. It has to do with zeros and poles. First order only has capacitor or an inductor, and the second order has a capacitor and an inductor, and that is your band pass filters and whatnot. This is where things start overlapping between linear systems, communications, and control systems. But for the most part, as far as the Bode plot is concerned, in the context of control systems, not worrying too much about the application, just get this part pretty strong and you should be set. Closed loop response, open loop response, and stability. So in the on-demand course, I start out the discussion of control systems by clearly defining what a closed loop transfer function is, what an open loop transfer function is, and what is a characteristic equation. Okay, so when you have a closed loop transfer function, which basically has a feedback, if you sever the feedback and put it as a single string, then that entire relationship between output and input becomes an open loop. And the denominator essentially of the closed loop transfer function equated to 0 becomes your characteristic equation. And there's a lot of information that we can draw from the characteristic equation, open loop and transfer and closed loop transfer function. Closed loop transfer functions are also called feedback systems. Open loop are feed forward. There's no feedback basically. In terms of stability, back in the day, before 2018, I believe, they used to have RH criteria, Ruth Hurwitz's criteria. I briefly talk about it in the course, and I tell you guys that from the standpoint of absolute stability of a control system, we have to do the RH test. Okay, thankfully, it's no longer part of the exam specification. They've explicitly removed it from the specification and also from the reference handbook. But what we are now being tested on, or that they have left within the specification in the context of system stability, is phase margin and gain margin. For the most part, phase margin and gain margin are very methodical. There are some mechanical steps that you need to take in order to come up with the numbers. Okay. But the math sometimes can be tricky because you are dealing with complex numbers over here, and figuring out the phase angle of complex numbers with numerators and denominator as a fraction is sometimes challenging for some students. And this is why I have slowed down in the on-demand course and the live training when we encounter this. And I strongly recommend you guys to do a complex number review 101 in order to have a good handle on this, because the theoretical portion of it obviously is challenging enough, but you don't want to lose point on the mathematical side of things. Okay. So understand and learn how you take a stepwise approach in figuring these out. And the last comment I'd like to make about phase margin and gain margin is that these are relative measures of stability. If a system has gain margin, which is a particular number, and the other one has gain margin, which is much larger than this number, then on a relative basis, this guy is more stable than this guy. Okay. But the absolute test of stability is RH criteria, which thankfully we don't have to worry about. Controller performance is one of the easiest topics, in my opinion, on control systems. You have the first order control system. You have the standard form that is provided to us in the reference handbook. They have an equation, a variation of the standard form with a time delay. First order control systems, fairly simple, straightforward. Second order control system model, again, they provide you a standard form. And then on top of that standard form, you have performance parameters, things like the peak time, settling time, and so on. Now, we may have to manipulate these equations and check out the NCEES sample exam for some examples. There's at least one question on the second order control system where they've provided you a transfer function and they've asked you for certain parameters. So you'd have to put the given transfer function in the standard form And once you are able to put it in the standard form, then you are able to extract omega, then you're able to extract the value of K and so on, and zeta and so on. Okay, and then from there onwards, it is just plug and chug for different types of performance parameters. The last but not the least is steady state error. So over here, as I've mentioned earlier, the tendency that students have is to search for steady state error, end up at the system type table, and get a warm and fuzzy feeling that I have hit a gold mine. Unfortunately, using that system table for steady state errors is not that straightforward. The reason being, you actually have to figure out the type of the system, okay, which takes a little bit additional work, and then interpreting that table itself is a challenge. My recommendation to students is always to use the Final Value Theorem, FVT, which we have practiced in the course. It is very simple and straightforward, and it simply tells you that the steady state error, okay, in the time domain is equal to limit of s goes to 0, s times e raised to power s, which is s times r of s divided by 1 plus g of s. R of s is your input, G of s is the block that you have. It can be multiple blocks all multiplied together. And when you do that, then figuring out the value of your steady state error becomes a lot easier. Okay. So this is a high level overview of control systems. I want you to pay attention to each and every important piece of this outline. And when you slice and dice it, you recognize that it is not that difficult, totally doable. Control systems is also important because it is not a very, very light topic. It is sort of a medium weightage topic. And as I mentioned earlier, some of you might not have taken any coursework in your undergraduate on control systems. But rest assured, if you go through the content that is provided in the on-demand course, have practiced from study guide quizzes and so on, you're going to be set. Okay. Or you're going to be far more confident than what you were before you got started. Okay. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE Electrical and PE Power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE Electrical and PE Power exam preparation programs, please visit my website, studyforfe.com.